Hi, so welcome to this lecture where we cover two topics here, groups and subgroups, very basic topics in algebra. So before we start off, let me just tell you something about what exactly we are doing. So what this study of groups and subgroups, what this does is, it tries to capture the kind of mathematics or arithmetic that we do every day. For example, we add numbers, we multiply numbers, things like those, okay, where we do operations. And these are specific examples. We can add real numbers, we can add rational numbers, we can multiply complex numbers. These are the kind of operations that we do all the time. Okay, there are other operations as well, but these are some of the ones that we carry out in our daily life all the time. But what this subject or the study of groups, especially groups, subgroups is kind of a subset of groups, and you can understand that from the word sub. But what groups does is to generalize this idea of having a set of numbers, for example, and then an operation on it. Okay. So, for example, if you add two real numbers, you would get another real number. Okay. So that's a law that we have when we do that operation of adding. Okay. Similarly for multiplication. So obviously the operations are not there just without any rule. They have to follow certain rules to make sense of the kind of things that we would be doing with it. So what this study of groups does is exactly what I said. It generalizes this idea of having sets and operations on them. And there will be rules. So these are the 4 rules, and I'll go over them one by one right now. So let's just come to the definition then. So what is a group? A group is a pair. The fancy mathematical word for pair is two-tuple. In other words, it has 2 coordinates, okay? And you write them in a bracket with separated by a comma. The first entry in the coordinate is a set. The set normally is denoted by the letter G for groups, okay? You can use any other letter. And the second entry in the coordinate is denotes an operation. For example, the addition operation, the multiplication operation. Okay, so it's a pair. In other words, 2 things put together, like the real numbers and addition. Okay, so it's a group, a two-tuple. This is called a group if this operation that I have put in here in the second entry is an operation which, what I mean by an operation is that if you take 2 elements from the set G, okay, then what this operation does is it sort of course it operates on the 2 numbers and turns them into another number, which we denote by A dot B. This dot is the same as this dot. Okay. So I just want to mention here this G, which is the first entry in this pair. This is a set, like real numbers. There's nothing more to it, just a set. Okay. And the operation, which is a dot, it's called a binary operation. It has a name. It has a binary. It's called the binary operation. Binary because it acts on 2 things. If you take 2 elements, G cross G is just the Cartesian product of G. In other words, you take the first element from G and then you take the other element, another element, B from G again. Then what this binary operation dot does is to act on both of them and turn them into another number. So for example, as I said, if you have R, the set as an example, which is the set of all real numbers, and if you had as a binary operation plus, then what you could do is you could pick 2 and 3, thinking of G as the set of real numbers. You can pick 2 numbers from R. The first one can be 2 and the second one can be 3. Then what this plus does is to turn this into 2 plus 3. Okay, you see, it's the same, the dot acts on it, and you put that dot in between the 2 numbers or the 2 elements that you have picked from the set. So that's your new number. Of course, we know it is 5, but that's the way it is written. When the plus or the operation, the binary operation, acts on a pair of elements from the set. Okay. Now, let me just tell you that this dot is a very general dot. Okay, it's a very general symbol. For various examples, you can have various binary operations. So, for example, as I said, for R, the set that I'm really considering when I'm taking R as a set and plus as the binary operation, I'm considering this tuple, this 2 tuple, or the pair. This is the set and this is the operation. You could take R with a multiplication. Okay, multiplication is also a binary operation. You can multiply 2 numbers and you would get 2 multiply 3. Okay, that would be another number. So this again is a tuple. It won't turn out to be a group, of course, and we will see why, but that's a different thing. We haven't come to the definition of a group yet, totally. But just to give you an example, that this dot here is representative of a very, of all operations that you can define, all binary operations that you can define on a set that you take. It's written in general as a dot, but really it depends on the example that you're working out, as to what that dot really means for that example. Okay, right. So let's come back. So a group will be a 2 tuple, where the first one is a set, the second one is a binary operation, such that it follows certain properties, 4 properties. The first one is called the closure property. And it means that for all AB that you take from G, in other words, if you take any 2 elements from the set, for example, 2 and 3 from the set R, and when you apply the binary operation on them, you get an element from G itself. You don't get an element from somewhere else. Okay. For example, when you take 2 and 3 from R, you apply plus as the binary operation on them and you get 5, which is again an element of R. So the product, it's also called a product by an abuse of notation or language, it's so far, the mathematics that we have learned, by product I mean a multiplication, but by abuse of language, an operation like this can also be referred to as A times B, or A product with B, or A multiplying B. So these are all terms that I'm using, which I use in my daily life to really mean real number multiplication or complex number multiplication. But in the general setting, I can apply those names as well. You just have to be careful to keep in mind that what we mean when we say those words, are we talking in the general sense, or are we talking for specific examples? When I'm talking about real numbers, multiplication would mean real number multiplications. If I'm talking about groups or in general terms, the word multiplication or product would mean a general dot like that. Okay, a binary operation. Multiplication would be a binary operation, or product would be a binary operation. Okay, so it depends on in which setting you are talking. Okay. So let's come to the first point that a group must satisfy to be a group, or this tuple must satisfy to become a group. Closure property. In other words, if you take two numbers or two elements from G, the product of them, again, see, I will probably be using the word product a lot, but now I mean in terms of the general setting. The product of them, or A dot B, should be an element of G. Now, of course, this point here is redundant. In other words, it's sort of understood from the way the binary operation is defined. It is defined that when you operate on a two tuple, A from B and G from A from G and B from G, if you operate on this with dot, the product should be in G. So really, you are defining binary operation in a manner such that the closure property holds in the definition itself. Okay, it's defined that way, that the product of A dot B should go to G. It can't go to anywhere else. Okay. But really, in a traditional sense, this point is always there when you define groups, and that's why I've just put in there. But really, it is almost included in the way we define the binary operation itself. Okay. So anyhow, this two tuples should satisfy the closure property. Okay. There is this property of associativity which it must satisfy as well. In other words, if you take any three elements from G, for example, 2, 3, 4 from real numbers, then it doesn't matter how or in which order you do the operation. So, for example, you can first product A with B, and whatever you get from that, of course, this should be an element of G, and that's how this is where the closure property comes in. When you product A and B, this is an element of G. So now you can product this element of G with another element of G, which is C. So first you product A and B, and then you product that result with C. If you do the operation in that order, it will be the same if you reverse the order of the operation. In other words, you first product B with C, and then whatever the result is, you product that with A. Okay. So for example, if you take 2, 3, and 4 from R, if you add 2 and 3 first, and then you add 4 to it, so 2 and 3 will be 5, and then adding 4 to it is 9. But it's the same as adding the last two first, 3 and 4 first, which is 7, and then if you add 2, which is the first element, it's 9 again. Okay, 7 plus 2 is 9. So it doesn't matter in which order you do the operation. If they match, if the two results match, then that's the law of associativity. So what this definition of group is saying is that in order to qualify as a group, this two tuple should also satisfy this law of associativity. Okay. This should happen for all ABC. In any choice of ABC that you take, I have taken 2, 3, 4 as an example. You can take 7, 5, 131, okay? And it should hold for that too, okay? Well, it should also satisfy this law of identity. In other words, there will be a very specific element, okay, which I will refer to as 1. And this is the symbol. It's written the same way as we write 1. But don't confuse again between in which setting we are talking. Okay. But anyway, let's first tell you what this point is. It should satisfy the law of identity. In other words, there will be an element. Don't mind how it is written now. I've written it like 1. But there exists an element which is written like 1 in G, such that if you take any other element from G, which I'm calling A, and you product that element with this very specific element in both from both sides. In other words, you product A with 1 and you product 1 with A. In both the cases, you should get your element that you have picked. And this, if this property holds for all element that you can pick A from G for this specific, one specific element, okay, this turns out to be a unique such element, then G dot is said to satisfy the law of identity. And this letter here, 1, or this symbol here, 1, is called the identity. Let me just rub out this. You have understood already. So 1 is the identity. In fact, this special element has a name. This is the identity. Identity. Okay, that's called the identity. So you must find an element like this from G, which follows this rule for all element in G. For example, when we were talking about real numbers in addition, what's the identity for real numbers with addition? The identity is 0, because remember, we're now using this as a binary operation. So if you pick any real number, for example 3, and if you add, in other words, you operate with it, this number 0 from both sides, in both the cases you will get 3. So they're all equal. Okay, so this remember, because we're talking about R plus, we have to substitute this dot with a plus now, because this is a specific example where the binary operation is the plus operation. Okay, so therefore this is the identity. This is the identity element for R plus, R addition. Okay, and 3 was just an example. Is any number that we have taken from R. You can take, as I said, you can take any number. You can take 100. You can take a billion, and it still remains the same. 0 follows the same, acts the same way with every number from R, and therefore this 0 is the identity. Okay, but as I said, in this course we will continue to write 1, or we will continue to denote the identity as the letter 1. Again, don't forget that it's written as 1, but really it doesn't mean I'm talking about 1 from real numbers. Okay, it turns when you're dealing with real numbers with the multiplication. Actually, I'll just put the star. We don't have to know what it is, why we need this right now. It just means that you omit the 0 from R. Okay, R contains 0, but you let go of the 0, and the set without the 0 is called R star. If you take this 2 tuple, where the first set is the set of all real numbers except 0, and the second one, which is the operation, the binary operation, is the multiplication operation. In this specific example, the identity is also written like 1. Okay, so again, depends on in which setting I'm using the letter 1. If I say 1 in this example, then I really mean the 1 that we have been using all this while, from our childhood, the way we learned mathematics. But if I say 1 for groups in a general setting, then I really mean a very general identity element for that group. Okay, right. And the fourth point that it must satisfy is this property of inverse, where every element from G, every element A from G, must have an inverse element. In other words, what I mean by an inverse element is that it's another element. It can be the same A, but we mean there will be another element, which we denote by A inverse. Okay. Again, I will say something about this, about the notation of this. But so for every A, you will get another element, which I will write as A to the power minus 1, such that if you product these two elements, they will give you the identity element for the group. Okay. If this happens for all elements, then this will be satisfying the property of inverse, or this fourth property. And of course, if G follows all the four properties at G dot, this two tuple follows all the four properties, then it will qualify as a group, and we will call it a group. Okay, let me just say something about this element here. Again, this is a notation that we have been using from our childhood, just to denote, for example, 2 inverse is half. This is how we have known this notation. Okay, but really, if I'm taking, again, let's take the example of, or sorry, I'll just keep that. I'll just keep that because this is what we are used to. So if I take the example of R plus, or R with addition, and I take 2, the letter of this element 2 from R, the question is, can I find an inverse in this group? Inverse of this element in this group? Well, in other words, I need to find another element such that if I operate, or if I operate this 2 with the new letter that let me call that letter X, okay, such that if I operate this 2 with the new letter from both sides, I should get my identity. What is my identity for this group? It was 0, remember? I just did it when we were doing this. So I need to find an element, another element, X, such that this holds. Of course, by dot, I mean the plus here, because this is a specific example where the dot is plus. So what's that element? We know what X is. It's -2. Right? So for 2, I can find the other element is -2, such that if I operate the addition on both, on this, 2 tuple from both sides, they give me my identity, which is 0 in this case. Okay. So by this notation, I may say that the inverse of 2 in this group is -2. Well, that's just absurd by whatever we have learned so far, but I can use this notation. I am choosing to call this A inverse, the other element that I find for A, which follows this property. I'm choosing to denote it by this letter in this general setting. So yes, in this example, that special letter for 2 is -2. But if I'm using this notation, then that special letter will be denoted as 2 inverse. Okay? So this really is the notation I'm using, and this is the actual element which carries out this property. Okay? So that's what I mean. So really, of course, as I said, when I'm using this group, where R star, R without 0 and multiplication, in that case, 2 inverse does turn out to be half. Because if I take 2 from R star, the element that I need to product with 2 from both sides to get 1, which is the identity in this group, is half. Okay? In this group, the identity was half. And for this group, that special element for 2, which carries out this property, was half. And so we called it 2 inverse is half. And for this particular group, the symbols or this particular notation here matches. But really, for other examples, it may seem absurd, but really not so absurd, because this is the notation for that special element, which is the 2 inverse. And this is the actual element which we have found, which would carry out this property. Okay. So, right. So summing up, so G will be a group, G dot will be a group if it follows all the 4 properties. So in other words, if you have to check whether something is a group or not, you would have to check if that 2 tuple follows all the 4 properties to finally announce it as a group. Okay. The group may follow an additional property such that if you take 2 elements from G and the order of the operation does not matter, in other words, if you product A with B, A on the left and B on the right, and if you product with B with A, in other words, B on the left and A on the right, and if they turn out to be equal for all A, B that you can pick from G, if that is a property, an additional property which G is following, in that case, this group would be called a commutative group or an abelian group. Okay, after the famous mathematician Abel. So this is an extra property. Sometimes a group may satisfy or may follow. In that case, it would be called a commutative group or an abelian group. For example, R plus. If you add 2 and 3, 2 on the left and 3 on the right, that's the same as adding 3 on the left and 2 on the right. Okay, so R plus would be an abelian group or a commutative group. Okay, not all groups will be commutative, and we will have an example here, which is matrix multiplication. Okay, if you multiply 2 matrices by matrix multiplication, you may not get the same result if you change the order of the multiplication. Okay. So this is an additional property. Now let's come to some examples. What are groups? As I said, this is a group, and we've just, while going through this, we've taken this as a model, as a prototype to show that this really is a group. Okay, all the properties that a group must satisfy is satisfied by these 2 tuples. So it's a group. Similarly, you can have integers with plus, and that would be a group. If you add 2 integers, that's an integer. Of course, it doesn't matter if you take 3 integers and if you carry out operations in whatever manner, first with any 2 and then the third one, they always give you the same result because after all, it's the addition. Okay, these are the simple additions and multiplications that we have known all this while. Okay, the set of all rational numbers without the 0, we have to omit the 0 here. Okay, and I'll tell you why. So if you have multiplication as the binary operation, the normal multiplication that we have known, if we have that with Q star, then that's a group because, again, you multiply 2 rational numbers, you get a rational number. Okay, so what's a rational number? Is a number like this, right? A number like this, P by Q. Okay, you can take away all the common factors between P and Q. And if you have R and S, okay, and if you multiply, really what you get is PR and QS, and that's a rational number. Okay, of course we have to have Q and S not equal to 0. Q and S cannot be 0. If Q and S are both not equal to 0, QS will not be 0. Okay, so it's a valid number, so it's a rational number. So the closure property would hold. Associativity again would hold because we've known this all this while that it doesn't matter in whether you multiply 2 numbers first and then the third one, or the next 2 first and then the first one. Multiplication always is associative. Identity. What's the identity element for this? I'm calling it a group because it's an example of a group, but I'm really proving that it is a group. So what's the identity element for this group? Okay, it's 1. Okay, it's 1 over 1. That's 1. Okay, that's the identity, and this is the binary operation we're using, multiplication. If you multiply 1 from the right or 1 from the left, you always get the element that you have picked from here, and you're checking it with the letter 1, okay, with the symbol 1, okay. So one is the identity element. Inverse. What's the inverse? Well, the inverse would be, now I need some element here such that I should get my identity for this, which was 1. Now, what's the element I need here to get me 1? Of course, I can just write Q over P. I think that would get me 1, because then you would have PQ and PQ on top and down, and that would cancel. But the thing that we need here is to understand that this P cannot be 0. Okay? I mean, here we say that Q cannot be 0 because P by Q has to be a valid number. But we did not say whether P cannot, in this, if you forget this, if you just look at P by Q, we needed Q to be not equal to 0. We had no restrictions on P. Okay? So P could be 0. But when you're looking for an inverse, you need to sort of reciprocate the number. And then here you require P to be not equal to 0. Okay? So therefore, to avoid this kind of a confusion, what we do is we actually take the star, which means we omit the 0 element from the rational numbers. So if there is no 0 in this Q star, P cannot be 0. Okay? Because if P is 0, then this whole number is 0. But of course, Q star cannot contain 0. Okay? So therefore, we omit this 0 from the beginning so that we can invert, the denominator and the numerator, or the reciprocate the number freely without any fear of having a 0 at the bottom. And therefore, this would be an inverse of this. Okay? In other words, P by Q inverse would be Q over P. Okay? And that's possible when P is not 0, which is made sure by the set that I have taken, which does not let P to be 0. Okay? So, and that's the secret, why we need the star here. Okay? Because we need to invert 0, and we cannot invert 0. We can't invert 0, so that's why we omit the 0 here. Similarly, you can check for complex numbers without the 0, and multiplication, for example. Okay? That would be another example of a group. Okay, let's come to some non-trivial examples of groups. These are fairly easy. If you take matrices, 2 cross 2 matrices, really you can take n cross n matrices as well, but let's just do with 2 cross 2 and it'll serve the purpose. With dot, a binary operation, what I mean by this dot is really matrix multiplication. So this set, GL2R, is really the set of all matrices, 2 cross 2 matrices, whose determinants are not 0. In other words, they are invertible, matrix invertible. You know what they are. So let's just work this out and tell you why this is a group. Okay, so I'm going to rub all of this out for the moment. And work out why this would be a group. So we are doing GL2R with matrix multiplication. Okay, so let's do the closure property first. If I take, that's the first property, the closure property. So if I take 2 matrices M and N, and I multiply them, okay, matrix multiply them. This is 2 cross 2, this is 2 cross 2, and we know when we multiply matrices, 2 cross 2 matrices both, we would get a 2 cross 2 matrix. So this is a 2 cross 2 matrix. Let's just write that down. This is from this special group that I've taken. So if I take any 2 matrices from this, I have to show that this belongs to this. I have to show that. How will I show? Of course, I know it is going to be a 2 cross 2 matrix, so there is no problem with that. But for this to be in this, really, it has to be shown that the determinant of this is also not 0. But that's easy, because if you take the determinant of Mn, I may omit dots once in a while. I'll try and put that, because if I omit, it really means it's in there. Okay, again, by some abuse of notation, sometimes people do omit it, sometimes to reduce notations purposefully, or sometimes, just by abuse of it. We know that determinant of this is really the determinant of M and determinant of N. And since these are elements from this, in other words, the determinant of M is not 0, the determinant of N is also not 0, so the product will be not 0. So therefore, the determinant of Mn is also not 0. And this proves that this product belongs to this group, and therefore the closure property holds. Okay. What about associativity? Well, associativity always holds. M, N, P, for example, if I take 3 elements, and we've all done this a lot of times, if I multiply 2 matrices first and then the third one, and it's the same as multiplying the second and the third first and then the first with it, that always holds. Okay, so associativity really holds. There's no issue with that. What about the identity element? Well, I think we all know this from our experience in dealing with matrices. I think the identity element, which I may call 1, okay, if I'm talking in general terms, but really because we already have a symbol for the identity element of this, it really is this element 1 0 0 1. That's a 2 cross 2 matrix, okay, and doesn't matter if you take any matrix from this. If you multiply M with this specific matrix from both sides, you will get M, and therefore this I acts like the identity element. So this is really the identity element. Okay, right. What about the inverse? Well, let's take an element from the set. I have to show that the inverse of this element exists. Well, we know the determinant is not 0, because this belongs to this would mean the determinant is not 0. And if the determinant is not 0, we know again from our experience that the inverse will exist. The inverse matrix exists. Okay, in other words, so for example, if M is this A, B, C, D, then we know the matrix inverse, as we have calculated it all our life, it's 1 divided by the determinant of M, which really is AD minus BC, and this is DA minus B and minus C. And you can check that this matrix, if you matrix multiply these two matrices, M with M inverse and M inverse with M, it always gets me this identity element. So therefore, this really is the inverse. Okay, so this therefore is a group. Okay, this is the identity element. Remember, I is the identity element. Well, in our notation for groups, you can write it as 1. Okay, if you understand what I'm saying here. Okay. All right. So that's a group. The question is it a commutative group or is it an abelian group? What about this element, 1, 1, 0, 1? What about these two elements, 1, 1, 1, 0? Do these two belong to this general linear group? Okay, which is called general linear group of order 2. GL2R, does it belong to this? Yes, it does, because they are both, they both do actually, because they are both 2 cross 2 matrices and the determinants are not 0. The determinant of this one is 1. Determinant of this one is -1, so they're both non-zero. So they are both elements of this. But if I product them like this, and if I reverse their order, I put this one first and this one second, will the two be equal? That's the question. Okay, let's do that. This one will be, so I'm just doing same, plain and simple matrix multiplication here. This is 2. This gets me 1, and this will be a 1 here, down here, and this one gives me a 0. Okay, let me see if this matches with this. So it's going to be 1. Oh, I have 1 here straight away, and they cannot be equal, okay? Because this is 1 multiplies with 1 is 1, and 1 multiplies with 0 to give me 0. I don't have to know what elements will be in here, but I know that they're not equal because these two did not match, okay? So it's not an abelian group because I can pick 2 elements from this which don't follow the commutativity. Okay, so it's not an abelian group. It's a group. So GL2R group, or let's write it as non-abelian group. And we've just proven that. We have another non-trivial example. Let's just work this out very quickly. So here is a group G, or not, I can't call it a group yet. We will work this out and see if it's a group. I'm claiming it is. We have a set G, which is given by complex numbers which satisfy this equation. Okay, and this binary operation here is just the complex multiplication. Okay, so let's see if this turns out to be a group. Okay. So G here are the roots of this equation. So what is this equation? X cubed minus 1 equals 0. Well, we all know how to solve this equation. It's really x minus 1 and x squared plus x plus 1 equals 0. So one of the roots is x is 1. And the other is, it's a product, so either this is 0 or this is 0. So the other 2 roots can be found from this quadratic equation, x squared plus x plus 1 is equal to 0. This gives me what? What are the 2 roots from here? It's minus 1 plus minus I root 3 by 2. And you can see that, okay? Let me call the one with, sorry, there's a half in there. Let me call this one as omega, and the other one with a negative sign, let me call that rho. Okay. Right. Why is this a group? Okay. So this group really is, have the 3 elements, the 3 roots of this equation are the one that we have always known. It's a complex or real number 1. And the other are omega, which is this complex number. And the other is rho, which is this complex number. They really are conjugates. You can see that plus and minus, okay? Complex conjugates. So this is a group. And with this, I have the complex multiplication, and this is the 2 tuple, and I need to show that this is a group. Okay, is it closed? Is this group closed? Otherwise, does the closure property hold? Let's try that. Let's try 1 multiplied with omega. If you multiply 1 with omega, it's complex multiplication. We know it is omega. If I multiply 1 with rho, again, complex multiplication, it's rho. If I multiply omega and rho, what is omega and rho? Well, what you can do is, you can see that omega square, what is omega square? If you just square it quickly, you will get rho. Really, let's see that. what I mean by square is multiplying this together again. Okay, so this multiplied by this, the same element with the complex multiplication there. Okay, so we will come to these notations in general terms. Okay, but really this is this multiplied with this. Okay, that's just that will turn out to be rho. Okay, that will turn out to be rho. I don't really have to do it because I already know it. Okay, you can try it. Okay, I'm sure you will get rho. Okay, so really omega rho is actually omega square. So this is omega square, and that really is because we know the rules of complex multiplication. This really is omega cube, and because omega is a root of this, so omega cube must be equal to 1. So this is equal to omega cube minus 1 is 0. So omega is 1. So you see, these are closed because 1 dot omega is an element of G because omega is an element of G. 1 dot rho is an element of G because rho is an element of G. Omega dot, if you product these two, omega dot rho is an element of G because 1 is an element of G. So just by, if you work this out by hand, you can show that it's a closed group, closed set with respect to this operation. What about associativity? Well, we are dealing with complex multiplication. That's always associative, and we've checked it a million times before. What about identity? Well, we know what the identity element of so associativity holds. Okay. What about identity? Well, 1, of course, is the one that we have always known belongs to the complex numbers. Really, it is just 1 plus I 0. That's the way in the complex form. And if you complex multiply this number with any number, let alone these two, you will get the number back, and we've actually shown it here in the first example itself. Okay, so one, the one that we have always known, okay, is the identity element here. Okay, and what about the inverse? So what's the inverse of 1? So there are only 3 elements. We can go over them one by one. What's the inverse of 1 here? Well, if you multiply 1 with 1, you will get 1. The idea was to find another element such that you got the identity back. And because we're taking the element 1, the other element is 1 itself. If you multiply 1 with 1, you get the identity, which is 1. Okay, that's pretty easy. What about if I take this one? Can I find an element here which should give me the identity, which is 1? Well, we just found it, rho. If I multiply this by rho, I get 1. And you can check that you can multiply it from both sides. Really, it's just it's multiplication of powers. Okay. Similarly, what if I take rho? Then by the same logic, omega is the inverse of rho because omega multiplies rho from both sides to give you 1. And so therefore, all elements have inverses. Okay. The inverse of 1 in this case is 1, and the inverse of omega in this case is rho, and similarly the inverse of rho is in this case omega. Okay, so the inverse property holds. Okay, the question is it associative? Yes, it is. Is this group commutative? Yes, it's a commutative group because we are dealing with complex multiplication, which we know is commutative, and we've done it so many times in our lives. Okay, so complex multiplication. So this is the complex multiplication that we're dealing with. Dot is commutative. So this group really, okay. So this is an abelian group. Okay, which really are sort of not very difficult, but still non-trivial examples of groups. Now, just a word of caution before we end this part of this lecture here, is that not all 2 tuples that you can pick, in other words, all 2 a set and an operation on it, not all such tuples, two tuples, will be groups. For example, if you pick the set of all natural numbers as your set and the subtraction as your operation, binary operation, then this is not a group, because if you pick two elements, 2 and 3 from n, and you operate them with the minus sign, which is the subtraction sign. So you operate 2 with 3 like this. You get minus 1, and we know that this does not belong to n. Okay, natural number. This is negative 1 is not a natural number. So the closure property does not hold, but the first property itself does not hold. Okay, because ultimately this product or this combination, whatever it comes to, will have to be an element of the set. So that's not holding here. What about n with plus? Well, now it holds. This closure property holds. But what about the inverse? Can I find? Sorry, is there an identity element in this n plus? There is no identity element. If you take 2 again, what's the element that you must add? The operation is addition to get 2. Well, I can't. There is no such product. No, I mean there is no such element. So there is no identity in this. So by that logic, this is not a group. Q with the rational numbers with multiplication, normal multiplication, again not a group, because as I said, 0 would be included in this, and for reasons which I've mentioned while we were doing Q star with this, if you include 0, then you can't find an inverse for 0. Okay, inverse for 0 would be 1 by 0, which is not valid. Okay, so the problem creeps in here is because with 0 here, 0 does not have an inverse. So if you find one element which does not have an inverse, so this will violate doesn't violate one of the rules. It means violate all the rules. So this for that you will not. It will not be a group. Okay. So here are just a couple of examples to show you that not all two tuples that you can pick will be a group. Okay. We will continue with subgroups in the next lecture. I think we will finish this here. Okay. Thank you.